Hello, I'm Professor Kitch from Cal Poly Pomona, and welcome to my series of geotechnical engineering webcasts. This particular webcast is an introduction to cone penetrometer testing. In this webcast, I'll provide a short overview of the cone penetration test, commonly called the CPT. My objective here is to provide a simple introduction to this test method. I'll describe the measurements taken during the test and explain how those measurements are made. Finally, I'll discuss some of the applications of the CPT test. I won't be discussing details of how to analyze test data in this webcast. CPT testing is most often performed using large truck-mounted rigs. These rigs have a hydraulic jack system to raise and level the truck, and the weight of the truck is used as a reaction mass when pushing the CPT probe into the ground. For sites that can't be accessed by a large truck-mounted rig, smaller track-mounted rigs are available. Very small track-mounted rigs, or rigs that fit on skid loaders, are also available for sites with very limited access. These smaller rigs are lightweight and must have an anchor system to hold them down, since the mass of the rig itself is not sufficient to provide the reaction needed to push the CPT probe into the ground. The red oval highlights one of the anchors of this particular track-mounted rig. Truck-mounted rigs are by far the most common rig used for CPT testing, and that's the rig that I'll be using to illustrate the CPT testing process in this webcast. However, the testing process is essentially the same regardless of what type of rig is used. The cone penetration test starts by locating the rig on site at the desired location. The rig is then leveled using external hydraulic jacks. The test consists of pushing an instrumented probe into the ground and measuring the forces the soil applies to the probe as it penetrates the ground. The probe is pushed into the soil using a hydraulic jack system located inside the truck. The jack system allows the probe to be pushed in at a steady rate of approximately 20 millimeters per second. As the probe is pushed into the ground, the jack is cycled up and down, and additional rods are added until the probe has reached the desired depth of investigation or until it can no longer be advanced. When the probe can no longer be pushed in, it has reached a point we call refusal. For most CPT rigs, the limiting factor on how deep the probe can be pushed is the mass of the truck against which the jack system pushes to advance the probe. Now, let's take a more detailed look at the CPT probe itself. The CPT probe consists of three separate parts: a 60-degree conical tip, which measures the end-bearing resistance to penetration, a friction sleeve, which measures the side friction, and between the cone tip and the friction sleeve is a flexible porous donut-shaped element through which pore pressure measurements are made. The rods are attached at the top of the probe and used to push the probe into the soil. The earliest CPT probes did not contain the pore pressure element and measured only tip resistance and side friction. The probe I'm showing you here is called a piezo cone because it measures pore pressure in addition to tip resistance and side friction. When we use this probe, the test is called the CPT-U test, with the U standing for pore pressure. Today, nearly all CPT probes are piezo cones, and the test is simply referred to as the CPT or the CPT test. There are a number of different size CPT cones as shown in this photo. All four of the cones shown here consist of a 60-degree conical tip, a friction sleeve, and a pore pressure element located just between the cone and the friction sleeve. The smallest cone shown here has a cross-sectional area of 2 square centimeters, which corresponds to a diameter of just 1.6 centimeters. Because of its small size, this cone can be used to delineate very thin soil layers. However, it has a relatively low load capacity due to its small size, and is generally used only in soft to medium clays or silts. The largest cone shown here, with a cross-sectional area of 40 square centimeters, is normally used in situations where gravel is expected. The most common size cone used for typical soil testing is the 10 square centimeter cone, outlined in red. Let's take a look at a cutaway section of the piezo cone and see how the measurements are made. Inside the probe, there's an inner rod that passes through the friction sleeve to the cone element. The cone is attached to the inner rod through a threaded connection. The inner rod is machined with a square shoulder partway down the shaft. The friction sleeve has a matching shoulder designed such that the friction sleeve bears on the inner rod at the shoulder. There are two load cells measuring vertical forces in the probe. The lower load cell measures the vertical force below the shoulder, and the upper load cell measures the vertical force above the shoulder. In addition to the load cells, the probe contains a pressure transducer to measure the pore pressure. When the probe is pushed into the ground, the cone must push the soil out of the way as the probe advances. The soil imparts a vertical load on the end of the cone as it is pushed out of the way. The cone transfers this end-bearing load to the inner rod. Because the load is applied at the end of the shaft, both load cells measure this end-bearing force. The soil at the side of the probe imparts a shear force along the outside of the friction sleeve. The friction sleeve transfers this side friction to the inner rod at the shoulder, where the friction sleeve and the inner rod meet. Therefore, the friction force is measured only by the upper load cell. By simultaneously reading both the upper and lower load cells, it is possible to separate the end-bearing load, measured by both load cells, from the side friction force, which is measured only by the upper load cell. The end bearing is reported as a stress called the cone resistance or tip resistance. The symbol Q sub C is used to represent the tip resistance, and it's equal to the measured end bearing load F sub C divided by the cross-sectional area of the cone A sub C. Q sub C is normally reported in units of tons per square foot or kilograms per square centimeter. The side friction is reported as a stress called the cone side friction or simply side friction. The symbol F sub SC is used to represent the side friction, and it is equal to the side friction force F sub S divided by the outside area of the friction sleeve A sub S. It is common to express the side friction by the friction ratio R sub F, which is simply the side friction F sub SC divided by the tip resistance Q sub C. The friction ratio is normally presented as a percentage. The pore pressure transducer is hydraulically connected to the flexible porous element sandwiched between the cone and the friction sleeve. It measures the pore pressure directly behind the cone as the probe is pushed into the soil. The pore pressure is reported in the same units as the tip resistance and the side friction. Some CPT probes measure the pore pressure at locations other than directly behind the cone, as shown here. The symbol U sub 2 is used to designate the pore pressure measured at this location, directly behind the cone. This is by far the most common location for measuring pore water pressure. So the measurements we get from the piezo cone are tip resistance, friction ratio, and pore pressure. As you can see from this animation, these three parameters are measured continuously as the probe is pushed into the soil. Because the CPT provides a continuous profile of measurements, it is very useful in delineating different soil layers. Note that the CPT readings above the green line are notably different from those below the line. The soil above the green line produces a relatively high tip resistance, a low friction ratio, and a very low pore pressure. In contrast, the soil below the green line produces a relatively low tip resistance, a high friction ratio, and a high pore pressure. We can use the CPT measurements to classify the soil based on its behavior. This is done using the chart developed by Robertson and Campanella in 1983. As you can see, this chart has different soil classification regions based on the measured friction ratio and tip resistance. The area in the upper left-hand corner of the classification chart is an area of high tip resistance and low friction ratio. Note that the area is labeled as a region of sands and gravels. Sands and gravels have high frictional resistance but no cohesion. Therefore, when the CPT probe is pushed into sands and gravels, they produce a relatively high tip resistance as the soil shears around the tip of the probe. However, once the cone tip has pushed the sand or gravel out of the way, the soil provides very little side friction on the probe because these soils have no cohesion. For this reason, soils exhibiting high tip resistance and low friction ratio are generally sands and gravels, as the chart indicates. Conversely, clay soils generally have lower frictional resistance and provide less tip resistance during CPT testing. However, due to the significant cohesion of such soils, they stick to the side of the friction sleeve and generate a relatively high friction ratio. Therefore, if we follow a line from the area of high tip resistance and low friction ratio in the upper left-hand corner of the classification chart down and to the right to an area of low tip resistance and high friction ratio, the soil classification changes from gravel and sand to silty sand to sandy silt to silty clay and finally to clay. Although our illustration here does not have numerical values for the CPT results, we can see that the upper soil has a high tip resistance with a low friction ratio, indicating that it is a sandy soil. The lower soil layer, by contrast, is characteristic of a clayey soil with low tip resistance and a relatively high friction ratio. Furthermore, we observe a large positive jump in pore pressure as the probe enters the second layer. This is an excess pore pressure generated during shearing of the soil as it passes around the cone. Because of this positive shear-induced excess pore pressure, we can deduce that the lower soil layer is probably a normally consolidated soil. It is important to note that this classification process is known as soil behavior type classification. We call it behavior type classification because it depends on the soil's behavior during SPT testing, not on the physical properties of grain size distribution and Atterberg limits used in a traditional unified soil classification system. In order to have a definitive classification of these soils according to the unified soil classification system, we would have to take samples and perform the proper lab test to determine grain size distribution and Atterberg limits. Another common variant of the CPT probe is the seismic cone. Like the piezo cone, this CPT probe measures tip resistance, side friction, and pore pressure. It is designated SCPTU, with the S standing for seismic. This probe contains a 3-axis geophone in addition to the load cells and pore pressure transducer in the piezo cone. The geophone allows the probe to detect seismic waves. Using the geophone and a shear wave source located at the ground surface, we can determine the shear wave velocity of the soil as a function of depth. The shear wave velocity is a particularly important variable in determining liquefaction potential for cohesionless soils. To make shear wave measurements, the CPT probe is pushed into the soil and tip resistance, side friction, and pore pressure measurements made, just as we've already described. However, at intervals where we want to measure the shear wave velocity, the probe is stopped. While the probe is stopped, a shear wave is generated at the ground surface. The shear wave source can be as simple as using a mallet to hit one of the truck supports, though it's very common today to use an automated shear wave generator which employs a solenoid attached permanently to the truck supports. The shear wave generated by the source propagates through the soil and is picked up by the geophone in the probe. Knowing the distance that the wave travels, L sub S1, and the arrival time of the wave from the source, T sub S1, we can compute the average shear wave velocity for the soil in this region, V sub S1, as L sub S1 divided by T sub S1. After completing the shear wave measurement, which only takes a few moments, the cone is advanced again and collects tip resistance and side friction data. We stop the cone at some deeper depth and generate another shear wave and repeat the measurements, this time determining L sub S2 and T sub S2. This time we can compute the average shear wave velocity for the soil between the first measurement point and the second measurement point, that is V sub S2, as the difference in the two travel distances divided by the difference in arrival times, as shown here. The actual computational method is slightly more complicated than this, but conceptually it's the same. The process is then repeated by stopping the cone at successive depths and generating shear waves until the CPT sounding has been completed. Using the data collected, we can then develop a plot of shear wave velocity as a function of depth. One of the characteristics of the CPT is that it does not take soil samples. At sites where disposal of drilling cuttings is a problem, either because of the location of the site or because the cuttings may be contaminated, this can be an advantage. However, in general, this is a shortcoming of the CPT test. There are, however, ways to mitigate this shortcoming. While the CPT probe itself cannot take soil samples, it is possible to attach a separate sampling device on the standard CPT push rods to retrieve soil samples using the same equipment used to push the CPT probe. Samples are collected using a CPT push sampler, which is approximately the same diameter as the CPT probe but longer. As shown in this cutaway drawing, the sampler consists of an inner rod and piston, an outer cylinder, and a locking mechanism. When the locking mechanism is engaged, the inner rod and piston move together with the outer cylinder. When the locking mechanism is released, the inner rod and piston move independently. By using the locking mechanism to lock or release the inner and outer parts of the sampler, it is possible to retrieve samples, as I'll show you next. I'll use this cutaway illustration to show how the push sampler retrieves samples. With the locking mechanism engaged, the sampler is pushed down to just above the location where we want to take a sample. We then release the locking mechanism and push the outer cylinder down. We then re-engage the locking mechanism and pull the entire sampler out of the ground, retrieving a sample with it. The sample is a relatively small sample, approximately 3.5 to 4 centimeters in diameter and 15 to 25 centimeters long, and it is considered a disturbed sample. If a sample is desired from a deeper depth at the same location, the sampler is cleaned, reset, and then pushed down the same hole to the next sampling depth. While samples retrieved in this way are small and disturbed, they are still suitable for characterization tests such as moisture content, grain size distribution, and Atterberg limits. As I mentioned earlier, the CPT can be used to determine a number of soil properties. This table lists a number of the possible soil properties that we can determine from CPT data. With the exception of the static pore water pressure, which is directly measured by the piezo cone, none of these soil properties comes from a direct CPT measurement. Instead, the values of these properties are correlated to the CPT measurements of tip resistance, friction ratio, pore pressure, and shear wave velocity. Several decades of field measurements have been used to generate these correlations. Some of these correlations are better than others, and the last two columns of this table gives you a qualitative idea of how good the correlations are for both the CPTU and the SCPTU tests. The actual correlations are presented in Robertson and Cabal 2012. In this presentation, I've tried to provide you an overview of cone penetrometer testing. We've seen how the cone penetrometer measurements are made, and I've described the process of classifying soil by behavior type using CPT data. Now let's review the attributes of the CPT test and summarize the test's application. The most common CPT probe in use is the piezo cone. This probe measures tip resistance, side friction, normally expressed as a friction ratio, and the pore pressure generated during testing. The CPT provides a continuous profile of the soil. For this reason, it's very good at identifying different soil layers. We can use this profile to classify soil based on behavior by comparing the relative magnitudes of tip resistance and side friction. The seismic cone measures shear wave velocity versus depth in addition to the measurements made by the piezo cone. Although this is a topic beyond the scope of this presentation, the seismic cone is particularly useful for liquefaction analysis. CPT testing is faster and therefore generally cheaper than drilling and sampling per lineal foot of soils logged. The CPT provides more consistent and reliable results than the standard penetration test because the loading conditions in the CPT are much better controlled than those in the SPT. One of the major shortcomings of the CPT is that it does not return a sample. Some push-type samplers have been developed which will allow CPT rigs to retrieve soil samples. However, these samplers have very limited capabilities. They are small and provide only disturbed samples. Samples cannot be taken while making CPT measurements. To take a sample, the rig must be moved and a separate push of the sampler in a new location used to retrieve the sample. For these reasons, the cone penetrometer does not usually replace drilling and sampling, but instead it complements it. There are many more sampling methods available for drill rigs than for CPT rigs. If laboratory strength and compressibility tests are needed, then high-quality undisturbed samples will have to be acquired, and these can be retrieved only through drilling and sampling. Because of the speed of CPT testing and the fact that it provides a continuous profile, Many geotechnical engineers recommend using CPT as the initial site investigation tool and following up with drilling and sampling after analyzing the CPT results. The CPT data can be used to determine the locations on site where high quality samples are needed, and in that way reduce the number of boreholes required. Here I have listed 4 of the key references for anyone who will be analyzing CPT data. The first reference is the ASTM standard for CPT testing and should be read by anyone performing CPT tests or analyzing CPT data. The second reference is an excellent handbook for engineers who specify or analyze CPT data. It covers testing methods and provides correlations for soil properties that you can determine using CPT data. Best of all, it's available as a free download from the website listed. Robertson and Campanella's seminal 1983 paper in the Canadian Geotechnical Journal is a must-read in order to understand the basis and limitations of soil behavior type classification. The final book listed is a thorough and in-depth presentation of CPT testing practice, but it does not include the newer information from the last 15 years of development. I hope you have found this webcast useful and that it has improved your understanding of how CPT testing is done and what information it can provide.